This is the 13th video lecture for the probability graduate level class. And we left off last time working with two continuous and independent random variables and found the PDF of x plus y, as we called it, the convolution between x and y. And I want to start there by looking at a specific type of example where both x and y are uniformly distributed. So let's recall if x and y, so x and y, are continuous and independent, then what we had was the PDF of x plus y evaluated today is equal to the interval from minus infinity to infinity. It was f sub y of y times f sub x of a minus y dy. And that's what we had. All right, that's great. As an example to look at, we're going to say let x and y be two uniformly distributed random variables with, or let's say on 0 to 1. So what that means is that f sub x of c is equal to f sub y of c, and what that's defined to be is defined to be 1. That's 1 over b minus a, if you remember for the uniform, if c is an element of 0 to 1, and it's 0 otherwise. Then let us find the PDF of x plus y acting on A. Okay. So, f of x plus y acting on A. Well, by definition of what we found, it's going to be that convolution. And here, let me write that down one more time. So minus infinity to infinity, f sub y of y, f sub x of a plus y. Now, here we're talking about integrating with respect to y. And just looking at f sub y of y, that part is going to be 0 most of the time. I didn't write down the y part. That's 0 most of the time. The only time it's not 0 is when y is in between 0 and 1. So that's going to affect this interval. It's limits. So from 0 to 1, and then over 0 to 1, this part is 1. So it's just f sub x of a plus y. It's not a plus y, it's a minus y. Yeah, that's right. dy. Let's make that change. All right. Now, this guy is going to be 0 most of the time. And the only time that it's not 0 is when a minus y is between 0 and 1. So we need a minus y to be sandwiched between 0 and 1. Let us solve here for y. So I'm going to subtract a from both sides. So minus a is less than or equal to minus y is less than or equal to 1 minus a. And then to solve for y, I am going to multiply everything by minus 1. So here, I've switched the directions of the inequality. This is a minus 1 is less than y is less than or equal to a. So if I think of pictorially what this is, when I just look at y, so here's the y-axis, is what I'm looking at. here's the a-axis. So again, y runs from 0 to 1. Now, I didn't say this already, but because we know that x's are between 0 and 1, and y's are between 0 and 1. When we talk about f of x plus y of a, we're talking about what can the a values run, where the a's are the output values for x plus y. Then a is between 0 and 2. So here's 2. We'll get this rectangular shape, it's not square. And then if I want this to be satisfied, working with this, we have two lines. If we solve for a, it says a is equal to y plus 1. And this right here is a is equal to y. So a is equal to y is this line. So 0, 0, and then we have a equal 1, y equal 1. That's this line. The a is equal to y plus 1. Well, when y is 0, a is going to be 1. When y is 1, a is going to be 2. So we have this line. If we're looking for the region where this happens, it turns out it's this middle region. So we just check a point out from here and find that it's the middle region. So like the point 0.5, so that point was 0.5, 1. You check this out, 0.51, so this is y, a. So 1 minus 0.5 is 0.5, and that is sandwiched in between 0 and 1. So it's this region we're talking about. So that's what we're integrating over. And so when I look at this integral, it kind of varies depending upon what a is. So if a runs from 0 to 1, then the y values, that's along here, the y values run from 0 to this line, okay, which is a. So here's where I am. So if 0 is less than or equal to a is less than or equal to 1, this PDF is equal to an interval from 0. I'm sorry. Yes, that's right. Interval from 0, as we said. So if a is between 0 and 1, the y values run from 0 to this line, which is a. So 0 to a. Here's where we are. So I have f sub x of a minus y. But a minus y and f of x of a minus y, remember that's either 0 or 1. So it's 1 in this region, dy. And that is equal to y evaluated from 0 to a, which is just equal to a. All right, what if a is between 1 and 2? If a is between 1 and 2, then we're looking at this region. Remember, here's 1, here's 2. This was y equal to a. And here this was y equal to, what was it? It was, or a equals to y plus 1. That's what this was. And so our f sub x plus y evaluated a. Well, if we're taking an a that runs from here, an a in between 1 and 2, the y values run from this line, which says that the y values run from a minus 1. So a minus 1 up to this line, which is y equal to 1. again, I have that f sub x of a minus y. And so what we have there is going to be 1, okay, in this region, and it's going to be 1, and so when we write down dy and integrate this, what we end up getting is y evaluated from a minus 1 to 1. And that leaves 1 minus the quantity a minus y, which equals to 2 minus a. So here's what we get for f sub x plus y of a. Well, first of all, I made those restrictions that a had to be between 0 and 2 because of what x had to be. Well, really a could be anything, but if a is less than 0, we get 0. If a was sandwiched in between 0 and 1, and what we got was just a. We did that earlier. If 0 is less than or equal to, 1 is less than a is less than or equal to 2, then here we get 2 minus a. And we get 0 outside of this, so if a is bigger than 2, that's what we get. So that is the PDF of x plus y for two uniformly independent random variables. And one thing I want to tell you is that you can see that this result isn't a uniform, the x plus y, it isn't a uniform random variable. But it turns out for many of our special types of random variables, if you add 2 of them together of the same type, they end up being that type again with maybe different parameters. And so that's what I want to look at next, the fact where that holds true. Okay. So as a fact, if x and y are independent Poisson random variables, with parameters lambda 1 and lambda 2, then x plus y is a Poisson random variable. With parameter lambda 1 plus lambda 2. Okay. Here, we can't use that previous fact that we were using before that had to do with the integral, the convolution between x and y, because x and y here are discrete random variables. So let us look how we can prove this. Here's the proof. We're going to let x and y be independent. Poisson random variables. And the parameter for x is called lambda. Remember, that's a number that's bigger than 0. Lambda is 1. And the parameter for y is lambda sub 2. That's some number greater than or equal to 0. It's fixed for y. Lambda 1 is fixed for x. Okay, even though this is discrete, we can do it. And so here's the way we think about doing it in terms of computing the PML of x plus y evaluated there. We say, well, this is the probability that x plus y is equal to x. And one way of viewing this is that it's the probability. Now, here, because x is Poisson, x runs from 0 to infinity, the little x's do. And same thing for y, they run from 0 to infinity. So A is running from 0 to infinity. Here, this is the same thing as, if you will, we can write this down as the union as k runs from 0 to a. The set where x is equal to a and y is equal to a minus k. So in this case, when x is equal to a and y is equal to a minus k, let me look at this for a second. So I think this should be a k here. Yes. So let's start off. When x is 0, the only way that you add x and y together to get a is y better be equal to a. What's another way that you can get that x and y adds up to a? Well, x could be 1 and y could be 1 less than a minus 1, I should say. So when you add them together, you get a. And so forth. So the union of these. Well, those are going to be mutually exclusive event. And so that ends up being the sum as k runs from 0 to, here it's a. Here, this is the probability that x is equal to k, comma, y is equal to a minus k. Now we have independence, so the probability of these two events happening is we got a sum, k runs from 1, not 1, but 0, to a. Probability x is equal to k, and times the probability y is equal to a minus k. And these are Poisson random variables, x and y are. So this is equal to the sum as k runs from 0 to a. And so this is nothing more than the PMF of x evaluated at k. So what would this be? This would be e to the minus lambda 1. Lambda 1 equals to the x normally, the PMF, but here x is being played by k, all over x factorial, so that's k factorial. Here, the probability of y is equal to a minus k. That's, remember, the PMF of y, and so it's Poisson, so it's going to be times e to the minus lambda sub 2 to the a minus k, all over a minus k factorial. Working with this, I can combine the e to the minus lambda 1, e minus lambda 2 to get a sum as k runs from 0 to a of e to the minus lambda 1 minus lambda 2. And here, I'll write down lambda sub 1 to the k, lambda sub 2 to the a minus k, all over k factorial is a minus k factorial. I can pull out the e to the minus lambda 1 minus lambda 2 because it doesn't depend on the index k. So that's e to the minus lambda 1 minus lambda 2. Sum as k runs from 0 up to a. And here I have, well, I'll rewrite this as 1 over k factorial a minus k factorial, and here I have lambda 1 to the k and lambda sub 2 to the a minus k. Now this sum is very close to looking like a form where we could use the binomial theorem. So that's what I want to work towards. So here I'll say, well, that's equal to e to the minus lambda 1 minus lambda 2. This is the sum, and this will be k equaling 0 to a. And what I'm going to do is I'm going to put an a factorial over what we have. So k factorial, a minus k factorial, and then I have lambda 1, and it was raised to the k, and lambda sub 2 raised to the a minus k. But I've stuck in this a factorial, which is a constant, so I'm going to divide by this a factorial here. This is equal to e to the minus lambda 1 minus lambda 2, all over a factorial. And this can be rewritten as the sum as k runs from 0 to a. This is nothing more than a combination. It's a choose k. Lambda sub 1 to the k, lambda sub 2 to the a minus k. That's where the binomial theorem comes into play. By the binomial theorem, this is equal to e to the minus lambda 1 minus lambda 2 all over a factorial. And then this, by the binomial theorem, is nothing more than, it will be lambda sub 1 plus lambda sub 2 to the a. And so let's remember what we just found. We found f sub x plus y of a. Now when you look at this, this is a probability mass function. We know a is equal to 0, 1, 2, 3, forever. And what this looks like, it looks like e to minus something. So that's e to the, this part right here can be considered e to the minus lambda 1 plus lambda 2 over a factorial, and this lambda 1 plus lambda 2 raised to a, that being the f of x plus y of a. That is the PMF. It's the right format. E to the minus positive number, fixed positive number, all over the variable of the function factorial, and then that positive number raised to the variable. That's exactly the PMF format for a Poisson random variable. So this is PMF of Poisson with parameter lambda 1 plus lambda 2. And that's what we wanted to show. So that ends this proof. Well, there's some more random variable combinations which kind of hold this form, and I'm just going to write those up as facts. Okay, so as a fact, as facts, the first one is that if x and y are independent binomial random variables, with parameters, so the parameter for x is m and p, and here n and p, so the number of times you do the Bernoulli experiment for y is n times, and the probability of success is p. The number of times you do the random experiment for x is m times, and the chance of success is p. Okay? They're independent. Then, x plus y is a binomial random variable. I'm counting the number of successes here. Random variable with parameter, I should say parameters, m plus n and p. Okay. Fact 2, I won't be able to get it all on this board, but, and I'm not going to prove either of these facts. But if x and y are independent normally distributed random variables, with parameters of independent normally distributed random, with parameters, okay, so mu sub 1 and sigma sub 1 squared, that's for x, and mu sub 2 and sigma sub 2 squared, that's for y. Then x plus y is normally distributed. With parameters mu1 plus mu2 and sigma 1 squared plus sigma 2 squared. I'm not going to prove those two facts. I'm just saying they're true statements. Next thing I want to talk about is something called the moment generating function. And it's going to be beneficial for us to find the expected value of a random variable raised to a power. And so here's its definition. It says, given a random variable x, the moment generating function of x is denoted by phi sub x of t and given by phi sub x of t is equal to the expected value of the quantity e raised to the tx. So phi sub x of t is a function, a moment generating function, is a function of t. I've got a little bit more to say. Okay. So phi sub x of t can be defined, depending upon whether x is discrete or continuous, is the sum, so it's the expected value, over all x values of e t x f of x, where x is discrete. And of course, f of x will mean the PMF of x. and it's equal to the integral from minus infinity to infinity of e sub t of x, f of x dx, if x is continuous. And of course, we're defining it here for a single variable, and it turns out you could define it for a joint moment generating functions. You have more than one variable. But anyway, we're looking at a single case right now. And so we assume phi sub x of t is defined for some interval let's say minus b to b, which contains 0. So our t values are in here. We're assuming that this function exists. All right, well, I want to do some facts about the moment generating function and then do some examples. So as a fact, if you take the nth derivative of the moment generating function, that's the same thing as the expected value of x raised to the nth power times e to tx. Okay. So this is the moment generating function. That's its derivative. There we have the answer. So this proof is done by induction. Proof is by induction. Remember what we do for induction, we show that it's true for n equal to 1, and then we show it's true for, or we assume it's true for n equal to an arbitrary fixed k. We must show, based on that it's true for n equal to k plus 1. So here, for n equal to 1, we want to show that the first derivative is equal to the expected value of x times e to tx. Okay. Well, no, phi sub x of t is equal to the expected value of e to tx. Okay. So, if you take the derivative with respect to t, this is equal to the derivative with respect to t of e to t x. And this is either, whether x is discrete or continuous, this is going to be a either a sum or an integral, and we can bring the derivative inside that sum or integral, and we end up getting the expected value of the derivative with respect to t of e to tx. Now, the derivative of e to the something, expected variable, x here is considered to be a constant. The answer to this, expected value states that, the derivative of e to the something is e to the something, and then you take the derivative of this. Now, I'm taking the derivative of this with respect to t. So t is a variable, x is constant. So I'll write down, by the chain rule, the derivative of tx, but that's just x. So the statement is true when n is equal to 1. Now, we assume the statement is true. We assume phi sub x of t, you take the kth derivative, and that's equal to the expected value of x to the k e to x. This is n equals to k. So what we're looking to do is show that it's true for n equal to k plus 1. That is, we must show that the k plus 1 derivative of phi sub x of t is equal to the expected value of x to the k plus 1 e to the tx. Well, note, what is the k plus 1 derivative of the moment generating function? Well, really, it's the kth derivative. It's its derivative. So that's the derivative with respect to t. And what was the derivative? What's the kth derivative of the moment generating function? Well, it's the expected value by assumption of x to the k e to the t x. And then again, I can pull this derivative inside. This is, so I do that. When I'm taking the derivative of this function with respect to t, x to the k is a constant, so we just write it down. Got expected value. I write down x to the k. And then I've got to take the derivative of e to the tx with respect to k, with respect to t. But again, that's e to the tx, and then we're taking the derivative with respect to t by the chain rule. I've got to take the derivative of tx, which is just x. And so that's equal to the expected value of x to the k plus 1 e to the tx, and that's what I wanted to show. So that's the proof. By induction, we have the formula. Okay, well, we want to look at what we get when we evaluate this to 0, and it's very easy to see what we're going to get. Remember, we're assuming that this moment generating function is defined at 0. Well, at least we're going to evaluate the nth derivative of the moment generating function 0. So here's the fact. Very simple. Phi, the nth derivative of phi sub x of 0 equals to the expected value of x and n. Very easily shown. Here's the proof. So we're going to I'll write out a little bit of words. B, the moment generating function, so the MGF, that's what we abbreviate moment generating function, of x. Then by the previous fact, phi sub x, the nth derivative of it, well, that's the expected value of x raised to the n e sub tx. So, if you evaluate the nth derivative at 0, this is e, so I'm letting t be 0. This is x to the n e to the 0x, which is the expected value. Well, 0 times x is 0. E to the 0 is just 1. So this is the expected value of x to the n. Well, that's what we wanted to prove. So there it is. Okay. All right. I'd like to look at some examples where we compute the moment generating function for specific types of random variables. So, as a fact, if x is a binomial random variable, with parameters n and p, then the moment generating function of x is piece of x of t equaling to, so I think it's p times e raised to t, and I think it's plus 1 minus p, all that raised to the n. Remember what a binomial random variable is you perform a Bernoulli experiment n number of times, and you count the number of successes with the chance of successes. So we're saying this is the moment generating function. So let's make sure that's right. So proof of it. So let x be a binomial random variable with parameters n and p. Then, then the MGF is phi sub x of t equal to the expected value of e to the tx, that's its definition, which is a sum. Okay. So here, what can x run from? X can run from 0 up to n of e to the t sub x, and here we have f of x. And so let me remember what the probability mass function is for a binomial. So x running from 0 to n, e raised to the tx. Okay, this was the number of times you did it. Choose the number of successes, p to the x, and then 1 minus p to the n minus x. That's what we have. Okay, so I'll rewrite this as the sum as x runs from 0 to n. And this is n choose x. Here I'll rewrite this as e to the t times p raised to the x, and then 1 minus p to the n minus x. Wonderful. Now, very quickly we can see if we apply, this is in the right setting for us to apply the binomial theorem, what we end up getting is e to the t times p plus 1 minus p, and then this would be raised to the n. And that's what we wanted to get. Wonderful. Well, wait a minute. I remember things about the binomial random variable. Like I remember its expected value. And so its expected value was n times 1. So note, the expected value, well, if I were to take the first derivative of t, the first derivative of phi of t, moment generating function. So here's what I'm looking at. Okay? Now I take this first derivative with respect to t. So what I'm looking at is something raised to a power. So I write down this as derivative, bring down the power, so something raised to 1 less power, and then I have to take the derivative of what I have in the inside by the chain rule. And so I'm taking the derivative with respect to t. And so I get e sub t raised to the e sub t times p. So just this term. So the derivative with respect to t1 is nothing, because it's constant. Same thing for p. The derivative of p times e to the t with respect to t, this is a constant, so I'll just write it down, and the derivative of e to the t is just e to t. So if I take this derivative and evaluate it at 0, remember that is the expected value of x. So let me write that down here. X is the first derivative here. So I'm evaluating where t is 0. So this is n, this t is 0, so I get p, because e to the 0 is just 1. And then here's plus 1 minus p. Okay. Here this is e to the 0, and then p. And so this is n. P minus p is nothing, so this is just times 1. And then e to the 0 is 1, and then p, so we end up getting p. Hey, that's what we wanted to get. So we're verifying the fact that the expected value of x is the moment generating function's derivative evaluated at 0. Work for the binomial. We'll use it. Okay, let's talk about the variance. So, also, phi, or let's say expected value of x squared is equal to phi sub x double prime evaluated at 0. Now, note phi sub x prime evaluated at t, we just did that, and I've got it written down here. N, I'll rewrite it this way, times e to the t times p, all that times e to the t times p plus 1 minus p to the n minus 1. We did that just a few seconds ago. So if I take the second derivative, the derivative of the first derivative, here I have an expression times another expression. I'm trying to take the derivative with respect to t. What we do that, the way we do that is use the product rule. So I write down the first, and I take the derivative of the second. This is the second, so I'm going to write down. I'm going to use the power rule. So I'm going to write down n minus 1, the sum of the power, the something raised to 1 less power. Okay. Now I take the derivative of the inside with respect to t, and that's e to the tp. E to the t times p. Plus, so I'm not done, so I've written down the first and the second. Now what I do is I write down the second. And I take the derivative first, and so this is going to be n e to the t p. So, if I evaluate this at 0, okay, so I'm letting t be 0. So here, this is n p times n minus 1. Here, this is going to be times p plus 1 minus p times p. And then plus, here, I'm letting t be, oh, I made a mistake here. This should be to the n minus 2. Okay. This is going to be p plus 1 minus p to the n minus 1. Here, this is n. This is 1, so p. So that's equal to, so here this is n, well, write down n, p squared times n minus 1, that's what that is, plus this was n p, okay? And so that's equal to, so I think it's n squared p squared minus n p squared plus np. And what that is that's the expected value of x squared by our fact dealing with the moment generating function's derivative evaluated at 0. So the variance of x is, remember, it's equal to the expected value of x squared minus the expected value of x to b squared. We calculated this earlier. The first thing we got here on the board still is n squared p squared minus np squared plus np. minus, what this was np to b squared, so it's n squared to p squared. These two guys cancel, so what I'm left with is np minus np squared. And when I factor out an n and a p, I'm left with 1 minus p, and that is exactly the variance of a binomial with parameters n and p. Okay, let's do one more example, and then we'll call it quits. For this lecture. So as a fact, if x is a Poisson random variable, with parameter lambda, then the moment generating function of x is phi sub x of t, which is equal to, so here I think it's e to the, look, lambda times e to the t minus 1. Again, we're going to let x be Poisson with parameter lambda. Then, remember, phi sub x of t by definition is equal to the expected value of e to the tx, which is going to be equal to the sum. In this case, x runs from Poisson 0 to infinity of e to the tx. Here's where I should put f of x. Well, that's e to the minus lambda, lambda to the x all over x factorial. From this spot, I'm going to pull out the e to the minus lambda. So if I do that, this is equal to e to the minus lambda, and then I'd have the sum as x runs from 0 to infinity. It would be e to the t x lambda to the x all over x factorial, which I'll rewrite as e to the minus lambda. Sum, here I'll combine the top terms to get e to the t lambda all raised to the x over x factorial. And using Taylor's theorem here, this is equal to e to the minus lambda, and this is from e to the t lambda. That's what this is using Taylor's theorem. And then this is e to the minus lambda plus lambda times e to the t, which we can rewrite as e to the lambda, factoring out a lambda of the exponents, e to the t minus 1. And that's what we're trying to get. Okay, very quickly, note here that phi sub x, for this particular phi, of t's derivative, so the derivative of this guy, derivative of e to the something, is going to be e to the something minus 1. So I'm working here to get the expected value of x, where x is Poisson. I'm taking the derivative of its moment generating function, I'm going to evaluate that 0. What's the derivative of e to the something? It's e to the something times the derivative of something. The derivative of this is going to be lambda e to the t. Okay? So when I evaluate this at 0, I get e, remember I'm evaluating at t be 0. So here is e to the 0, that's 1 minus 1. And then this is lambda times e to the 0, which is 1. 1 minus 1 is 0. Lambda times 0 is 0. This is going to be 1 times lambda times 1. And that's lambda. And that indeed was the expected value of a Poisson random variable, x, with parameter lambda. Well, let's try to find the variance. And then we'll be done for today, for this video lecture. Got fuzzy. Okay, good. That's good. Now, note the second derivative is equal to the derivative of this. So let me write down what the first derivative was. So the first derivative was lambda e to the t times, so this will e to the lambda times e to the t minus 1. Okay, so we need to take its derivative with respect to t. So I'm going to use product rule again. So I'll write down the first. The derivative of the second is e to the lambda times e to the t minus 1 times the derivative of this, which is lambda times e to the t, and plus, now we write down the second, times the derivative first, which is lambda e to the t. And now, if I evaluate this at 0, t is 0, so I'm looking here, t is 0, I get lambda e to the lambda times 0, lambda e to the 0. Here this is plus e to the lambda, and this is 1 minus 1. Here's lambda e to the 0, just 1 on short at that time. And then this is going to be lambda times lambda is lambda squared plus, here this is a lambda. Okay. So when this is equal to the expected value of x squared. So the variance of x, which Poisson is expected value of x squared minus expected value of x, and that's lambda squared plus lambda minus, well, this was lambda to be squared, so we just get lambda, and that is the right answer. Well, I guess I'm not proving anything, but it's verifying that our fact is working for Poisson, and it was another way to compute using the moment-generating function. It's another way to compute the expected value of a random variable and its variance. Thank you very much.